If you are a scientist in optics, please never use these two words in your paper. Mode can mean different things, but in the photonic context, it is usually an eigenmode. But an anapole is not an eigenmode. It is a state. And the fact that many other people do it is not an argument. This mistake was introduced historically when Anapole just appeared and not everything was clear. Scientists also made mistakes, we are all people, but the point is to admit your mistakes. And unfortunately, the journal system is not really made for introducing corrections. You need to go through the whole submission procedure again, and the correction not really will be visible unless you visit the journal website. Unfortunately, too little attention is also paid to write strict definitions, which then leads to careless use of terms and confusion. Formulating definitions is difficult. There can be several definitions, you need to take all the possible constraints into account, but it's also very important that words do not lose their meaning. Why the hell there are so many people in physics afraid to write definitions in their papers? Not like somewhere in the text, but definition, colon, and definition. Let us try to do this here, at least for Anapole. I do not claim anything, my definition can be proved further. In spherical nanostructures, it's easy to define Anapole. You just consider the Mie-scattering problem. You want to obtain what happens when a plane wave is scattered by a sphere of any size. This means you decompose everything in the basis of vector spherical harmonics. It is kind of like Fourier decomposition, but in 3D space and for vector fields. You decompose the incident field, the internal field, and the scattered field. Write the Maxwell boundary conditions, and voila, you have the solution for the scattered fields decomposed into vector spherical harmonics, and in other words, multiples. Multiples is not always exactly means vector spherical harmonic, but so the scattering cross-section, the intensity of scattered field, have contributions from different multiples. This is shown here by the colorful lines. So what is an Anapole state? It is simply the situation when the contribution of a particular multiple is zero. Basically, this sphere does not scatter in this particular multiple channel. It is just a zero of this function. Anapole can exist for any multiple, and there can be many Anapoles, I guess infinitely many, for a single one particular multiple. So there are many Anapoles for dipole, many Anapoles for quadrupole, many Anapoles for magnetic dipole and magnetic quadrupole, and so on. Okay, for a sphere, Anapole is just a zero of a scattering coefficient of a particular multiple. Then we can talk about what it means more generally. When we want to obtain the multipolar decomposition of some far field produced by some current, we basically take an integral of a particular form. See more about this in the links in the description. So a natural generalization would be an Anapole is a current distribution that does not radiate as a particular multiple. But the point is that, of course, if the current distribution corresponds to a quadrupole, it does not radiate as a dipole. It's not enough to define it like current distribution which doesn't radiate into a particular multiple. Like it should radiate, but it doesn't radiate. But what does multiple even mean here? Multiples are basically irreducible representations of symmetry group of a sphere, and after some considerations, this means that if the current transforms as a particular multiple, it can only radiate as this particular multiple. Kind of tautological, but still. And transforms as a particular multiple means that it belongs to some particular irreducible representation of this group, O3 group. So after all, my suggestion for a definition is here. Anyway, in the comments you can suggest a better definition. This one may sound somewhat sophisticated, and I could also be making a mistake. I didn't discuss the toroidal stuff yet. There is a reason when we're talking about a toroidal dipole, just dipole plus toroidal dipole, it is an approximation, and what I was talking about didn't require any approximations at all. So toroidal dipole stuff can probably help you to understand some picture, but it's not really related to a strict definition. One more thing I want to mention is that I'm not 100% sure about whether anapoles exist in non-spherical particles in the strict sense. I mean a clear zero, not 10 in power minus 10 or something. In principle, nothing contradicts it. It should exist, but in reality, I don't remember seeing a strict, not numerical confirmation. Tell me if you know one, please, but I guess it should exist also in non-spherical particles as well. Probably not always it would be a clean anapole, so as for me, it is an open question for me. And the most interesting part is that if you go back to sphere again and plot mi coefficient, but in complex plane, you will see that there are also zeros at complex frequencies. So kind of complex anapoles. They have also been discussed in the literature, links in the description. Fun fact, I didn't check this properly either, but if you add absorption to the material, at some points these complex zeros start to eat complex poles. So eigenmode disappears, it gets absorbed, and it seems like it happens with the help of these complex zeros. But I didn't really look a lot into this story, but apparently this happens. Thank you for listening. You see, I'm a little bit tired today, but still I guess this video should be made, and sorry for my accent. It could be much worse if I don't try to make it better.